Sorry, I've been having technical. So let me just yes, let me share the slide we were on yesterday so that we just complete it. I think we have about
Can you see the?
we have about 6 to 7
Yes, sir.
slides to go yesterday.
Currently sharing
Please, is this where we stopped yesterday? I think this is where we stopped yesterday, Bo.
Yes, sir.
Yes. Now, it's on the slideshow.
So I think we were on we were discussing t-test when the network came between us.
Yes, sir, it is.
So I think we described single sample t-test.
Yes, sir, it's not there.
Okay, just to recap, we said t-test is used for comparing mean values. That if you have mean values and you want to compare them, you can use
overview of basic statistics.
I'm here. Something is interfering with this.
Researchers, biomedical researchers.
Sorry, I think there is something interfering with our presentation.
With research. So
Okay, hello, sir. Maybe you switched on an audio device. Try pausing it.
Yes, I just realized because the initial link I clicked on was the YouTube, so I had to. Okay, I think it's okay now. All right. The slide is moving, Paul.
Yes, sir.
Yes, sir.
All right. So we said if you want to compare mean values, you have two broad options. And these options will depend on whether you are dealing with two mean values or more than two mean values. If the mean values are two, we said you use student t-test. So student t-test is of three types: the single sample t-test, paired t-test, and the independent t-test. We describe single sample t-test as the one that is used when we are comparing sample mean versus population mean. We have two mean values, one coming from the sample and the other one coming from the population. If you want to compare them to know whether they are comparable, whether there is significant difference between them or not, it is single sample t-test that we are going to use. Then we said paired t-test. The paired sample t-test, we said, is for comparing mean of paired samples, meaning that we have one sample, but each member in that sample has two readings, either readings from different variables or reading of the same variable but taken at different time interval. For example, we say you have a group of malnourished children, you take their weight and you give them nutritional intervention. After your intervention, you take the weight again. Now, if you want to know whether your intervention has worked or not, you compare your baseline weight with the post-intervention weight. So in this case, you can use paired t-test because you have a single sample that each member of that sample is having two readings. So that is why it is called paired t-test. You can also use it, for example, if you want to compare students' performance between first CA and second CA. You can also use it to compare students' performance between two courses or two subjects, maybe their performance in surgery versus their performance in medicine. In any of this, if you look at it, you see that it is the same student that is having two readings, one for surgery and one for medicine, for example, or one for first CA and the other one for second CA. So this is where you use paired t-test. independent t-test is used if you are having two independent samples and you want to compare the mean values. For example, you have mean weight of children from rural area and you have mean weight of children from urban area. These are two independent samples. So you can use, if you want to compare their mean values, you use student t-test. If you want to compare mean weight, for example, between males and females, the same thing, you can use student t-test because they are independent samples. So t-test is a parametric test. Please, we should take note, it is a parametric test, meaning that it is only applicable if the distribution of the data is normal. So if data is normally distributed, that is when we can use t-test. But if data is skewed, meaning that there are extreme values, either extremely large or extremely low, we cannot use t-test because it will give us misleading result. Just like we saw when we try to use mean on a data that has skewed distribution, we saw that it gave us a misleading result. So that is why we say if data is skewed and you want to know the average, don't use mean, use median, because median is less affected by extreme values. So the same thing, if you have two mean values, you want to compare them, but then you realize the distribution of that data is skewed, it's not normal. It means you cannot use t-test. So the option is to use a non-parametric test. T-test is a parametric test. So the option, if the data is skewed, you use non-parametric test because non-parametric test is less affected by extreme values. So if data is skewed, you can still use non-parametric test because they are less affected by the distribution of the data. So for paired t-test, the counterpart is Wilcoxon sign rank. So if you want to use t-test, paired t-test, and you realize you cannot use it because the data is already skewed, then the option is now to use what? Wilcoxon test. That is Wilcoxon sign rank test. So that is the one that will allow you to compare mean values of paired sample when the distribution is skewed. For independent t-test, the counterpart is Mann-Whitney U. You want to use independent t-test to compare mean values coming from two independent samples. You realize, oh, the data is skewed. Then your option is to use Mann-Whitney U test because Mann-Whitney U test is a non-parametric test. Non-parametric tests, like we said, are tests that are less affected by the distribution of the data. So if data is skewed, it is better you use a non-parametric test. So we said t-test is only used for comparing two mean values. If the mean values are more than two, if the mean values you are comparing is for more than two groups, please, you cannot use t-test. The option is to use ANOVA, as we are going to see in the next slide. So t-test, when you use computer, for example, to compare means, so t-test value is usually given with p-value. So the same thing, don't so much bother, like we said, when we're trying to interpret chi-square test, we said we shouldn't so much bother on the value of the chi-square test, but we should focus on the p-value or the 95% confidence interval. The same thing applies here. If we are using t-test, we are going to have at least two values. One value representing the t-test, that is the test statistic value, and the other one is the p-value. So we should focus on the p-value. That p-value, is it less than 0.05? If it is, then we conclude there is statistically significant difference between the mean values. If it is not less than 0.05, we conclude there is no statistically significant difference between the two mean values. The same thing applies to the if we are using 95% confidence interval. You know, yesterday we mentioned two things. We said in that confidence interval, for it to be significant, the value we are looking for must fall within the range of the confidence interval. That is one. And two, the range of the confidence interval does not contain null value. And then for odds ratio and relative width, the null value is 1. That is for regression. If you are looking at regression, the null value is 1. And we said the null value for mean is 0. That means if you are trying to compare means and you want to use 95% confidence interval for interpretation instead of p-value, then all you are going to look for is, first of all, that mean value. Does it fall within the range of the 95% confidence interval? And that range, does it include 0? Because we say for mean, the null value is 0. For odds ratio, the null value is 1. So this table is just for example, let's say we want to compare mean antibody titer between males and females. Look at the mean for male 35.6, for female 47.2 with this standard deviation. Look at the result. The t-test value is not even given, but at least the p-value is given. They say p is 0.01. And our cutoff for interpreting p-value yesterday we said is what? 0.05. So 0.01 is less than 0.05, which means it is what? Statistically significant. So that means there is a difference between antibody titer of males and female as far as this result is concerned. So this one is just to guide us. If you are using SPSS and you want to compare, you want to use t-test, these are the steps. You go to analyze, compare means, independent t-test, and so on and so forth. But this is not practically on data analysis. This is on overview of statistics. So this is the result you get when you run t-tests using SPSS, for example. This is the output. The computer will give you this as output. The computer will not do the interpretation for you. You are the one that will do the interpretation. I don't know whether this slide should have been included or not, but anyway, I will still explain it. We will have at least a couple of people that will follow. You see, in this output, there are two tables. One is the one for the descriptive statistic that gives the mean values. The mean value for intervention group and the mean value for the control group. So this is the independent t-test analysis result. So when you look at this column, the one that you see, that is the sixth column, where you see sig two-tailed. That is the p-value. That is the column for p-value. And you can see we have two p-values. One 0.184 and the one below also 0.184. They are the same, but they are not always the same. Sometimes you see the one above different from the one below, and only one of them should be used. So that means you need to know which one to use at any given time. So the guide to which p-value we are to use in this table is from this third column. Third column from the left, you see where you just see sig, no two-tailed written. The first column, second, the one with F, and then the third, where you see sig. That is the Levin's test for equality of variances. So before you know which of the p-values to use under that sig two-tailed, you must find out whether the variances are equal or they are not equal. Because one of the requirements, one of the assumptions when you are using t-test is that variances are equal. It's one of the assumptions. You know, even in chemistry, physics, when we're doing practical, they will tell you, okay, assumptions, precautions, source of error. So if you are using t-test, also there are assumptions. One of such assumptions is that you are assuming that the variances are equal. So when you come to interpret your result, you must find out whether equal variances are assumed or not. So the way to find out is to look at this Leibniz test of equality of variances. You look at the p-value for that Leibniz test, which is the value you have under this column that has sig. Now look at the p-value. The p-value is 0.347. 0.347 is clearly above 0.05. So that means there is no significant difference between the variances. So if there is no significant difference between the variances, invariably all we are saying is that what? The variances are what? Assumed to be equal, because there is no significant difference between them. So if the variances are assumed to be equal, you are free to use any of the p-values under this sig two-tailed. If you like, you use the one on top. If you like, you use the one below. In fact, once you see that the variances are assumed to be equal, you see that the p-values are similar. But if you look at this Leibniz test, let's say, for example, instead of this 0.347, the value that is here is 0.03. You see, 0.03 is less than 0.05. So that means there is significant difference between the variances. So if there is significant difference between the variances, that means equal variances are not assumed. That means the variances are not equal. So if the variances are not equal, it means you now look at this, the first column. You see that the first row is equal variances assumed. The second column, equal variances not assumed. So if the variances are not equal, you come to the second column, the one below, equal variances not assumed, and you look at its p-value. Whatever the p-value is, that is the p-value you are going to use. So that is how t-test is interpreted. You use paired t-test or independent t-test, doesn't matter. That is how it's interpreted. But once equal variances are assumed, no problem. Whether you use the one on top or below, the variances, the p-values are going to be the same anyway. So you can go ahead and now make your interpretation. So this is ANOVA. ANOVA, we say if now, you know, we said t-test is only used if the means are 2. So for ANOVA, if the means are more than 2, we cannot use t-test. So the option is to use ANOVA, that is analysis of variance. ANOVA is analysis of variance, and it is used to compare mean values that are more than 3. So if you have mean values of more than 2, that are more than 2, you have mean values of more than 2 groups, please use ANOVA. So ANOVA, there is one-way ANOVA and there is two-way ANOVA. One-way ANOVA is used if you are comparing means when the groups are defined by only one exposure. For example, if you are comparing mean hemoglobin concentration with respect to hemoglobin type, with respect to genotype, you see here you are comparing only based on genotype. Those ones that have SS, what is their mean? The one with AS, what is their mean? AA, what is their mean? AC, CC, and so on and so forth. Here, genotype is the only source of what? Exposure. So that is one-way ANOVA. two-way ANOVA is used if you are comparing mean values based on 2 or more exposures. So if you are comparing mean values, the other one we say for one-way ANOVA is if what you are comparing is just based on one factor. For example, genotype or blood group or sex. All these ones is one-way ANOVA. But if you are comparing mean values based on more than one exposure, for example, you are comparing mean values based on sex and genotype, it is two-way ANOVA. Or based on sex, genotype, and blood group, it is still two-way ANOVA. So this is it on this slide. So both one-way and two-way ANOVA compare mean values between groups and within group. What is meant by between group and within group? For example, if we have 3 groups, SS, AS, and AE. So two-way ANOVA will compare the mean difference between these 3 groups. That is 1. It will also compare it will also compare the values within each group. Because, for example, SS, maybe there are 20 patients that are SS. Their PCV or their hemoglobin concentration is not going to be the same. So it will compare that difference. So that is within group. Within each group, within SS, what is the difference? Within AS, what is the difference? Within AA, what is the difference? So that is how ANOVA works. So once the p-value is significant, there is no need to carry out a post hoc test, because there is what is called post hoc test. So if p-value is not significant here, I think there is mistake here. It is supposed to be once p-value is not significant. Because if you run ANOVA, it will show you if there is significant difference, you see that yes, the p-value is less than 0.05. So, but your next challenge is which group is responsible for that difference. For example, you compare mean values between AS, SS, and AA, and it shows you there is difference. So how do you know which of the groups is responsible for that significant difference? Is it the SS, is it the AS, or is it the AA? So that is done, that can be solved using post hoc test. So you do post hoc test, there is Turkeys and so on and so forth that you can use if you are using a computer to do that. So it will show you where the difference lies, which group is responsible for the difference. So the final thing we are going to briefly talk about is data presentation. Because whatever you do, you must be able to present it in a meaningful way that will attract the attention of whoever is interested in your research finding. So that means the data you are able to process and analyze can be presented in various ways. You can simply present it textually by just narrating your finding, especially if it is qualitative research. For example, interview, you can just narrate it, that is textual. You can present it numerical presentation, for example, mean value. You are able to get all the weights and you decide to just calculate the mean. You can write the mean value and the standard deviation. That is numerical presentation. You can also decide if the data is quite large. Maybe you are dealing with complex data or data that is a bit large, containing different variables. You can organize it in a table and present it in a tabular form. Yes, and then you can decide to use graph. So there are different type of graphs that can be used, and so on and so forth. So if you are presenting your data in numerical order, or even sometimes textual, it is important you arrange it either in ascending or descending order, depending on which one is. So if you are using table, because is almost inevitable the use of table, at least your social demographic characteristic, that is the biodata, is expected to be presented using table. So these are some of the principles just to guide you as you design your table. The table must have number, table 1, with its title, table 2, and so on and so forth. So that is why it must have title. Don't just put table 1 and then you plot your table and you move on. No. What is that table 1? Table 1, social demographic characteristics of respondent. Table 2, pattern of blah, 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 and so on and so forth. Then the columns and the rows must have heading. So you cannot have a table whereby the column, you look at the column header, there is nothing there. So one will not know what the column is representing. The same thing, row. Row is the horizontal one, while the column is the vertical. The dependent variables in a table usually are put within the column. So whatever you consider to be your dependent variable, yesterday we talked about what dependent variable is. So that is the one you are going to put within the column. Whereas the independent variable, you put it along the row. Percentages should be put close to the frequencies where necessary. The table should not be too large. Sometimes you see table cutting across 3 pages, 4 pages. Table 1, like that. So as much as possible, make your table, present it within 1 page. If it is so long that it cannot be presented within 1 page, you can break it. Table 1A, social demographic characteristics. Table 1B, social demographic characteristics continued, and so on and so forth. So each page, you put the table and you put the narration below the table. So as much as possible, vertical arrangement of, because table can be presented vertically or horizontally, but the vertical is preferred. And then you should put footnotes where necessary. So these are just examples of different types of graphs you can use. Pictogram usually is for laymen. If you have simple presentation to present to laymen, you can use it. Bar chart, we have either simple compound or component, as the case may be. So here it's good for presenting frequencies or sometimes even proportion, so you can match them. Pie charts, if the categories are few, you can use pie chart. But if the categories are many, maybe you have up to 7 categories and so on, please don't use pie chart, because it is going to, all the segments are going to be so narrow. Sometimes even the data level, you will not have, space to input it. So as much as possible, if once the categories are many, let's say more than 3, preferably use bar chart. Histogram for continuous data such as age, weight, and so on. Line diagram, it shows trends over time. For example, maybe utilization of something, first quarter, second quarter, third quarter, or 2020, 2021, and so on. And so it will show you, you will see whether something is rising or falling, or it is just plateau the way it is. Cumulative frequency, polygon, spot maps, box plots, stem and leaf, these ones are not commonly used, but the first few that we mentioned, spot maps, yes. During, if you are looking at outbreak, the distribution of cases within the community, you can actually use that, but that one is for another. So I think By and large, we have been able to discuss basics of statistics, and we have seen that it is a science that deals with data management and drawing conclusions from small observation to large observation. It's broadly classified into descriptive. If you are only interested in collecting data, analyzing and interpreting your findings, and we also have inferential. If in addition to interpreting your finding, you also want to draw conclusions. And we say when you do that, probability is there because your conclusion might be true or it might not be true. So that means there is issue of generating hypothesis, which must be tested. And we mentioned different areas we encounter inferential statistics. And also, we talked about the interpretation, when to use certain types of descriptive statistics. For example, we say in descriptive statistics, mainly it deals with measures of central tendency, which are measures of average, measures of dispersion, which are measures of variation, spread. And we said if the data is normally distributed, you want to calculate the mean, the average, preferably use mean. If it is not normally distributed, use median. For the measures of dispersion, we say if it is normally distributed, preferably use standard deviation or maybe variance. But if it is skewed, use interquartile range. For t-test also, we said if the data is normally distributed, you can use t-test. But if it is not normally distributed, is skewed, you use the counterparts. Either you use Mann-Whitney U or Wilcoxon sign rank. And we say ANOVA is used if we are comparing mean groups of more than mean of more than 2 groups. And ANOVA also, maybe I did not mention, but ANOVA also is for what? Normally distributed data. If data is not normally distributed, the counterpart, the non-parametric counterpart that should be used is Kruskal-Wallis test. Kruskal-Wallis, I don't know whether it's, I think it should be written, yes, it's here. So don't worry, it's in the slide, Kruskal-Wallis test. So by and large, I think we have come to the end of our discussion on basic research statistics. So if there are questions or observations, maybe we address a few that we can.
Okay, thank you so much, Professor, for this elaborate lecture. We so much appreciate your efforts. May Allah reward you abundantly. So we are going to take comment and questions. Please, one can write on the chat box, or you can also raise hand. We will allow you to unmute and talk. So the first question I'm having is from the parent. He's saying, good work, Prof. Please, how can one determine the normality of data and provide objective evidence of the same to an assessor?
Okay, so you can, the simple, I think I talked about it yesterday also, the simple check that you can run to know whether your data is normally distributed or not normally distributed.
Okay, thank you, sir. The next question.
You say if you have your mean, just get you, if you multiply your standard deviation by 2 and then subtract it from the mean.
Okay, thank you, Prof. Sir. The next question is saying, thank you, Prof, for the well-detailed presentation. I need more clarification on when to use post hoc test and ANOVA test. Thank you. The question is from Abdulaziz Balarabi. Hello, sir.
Hello?
Yes, sir, we can hear you.
Yes, it was a call that came in and disrupted because I'm
Okay,
using
sir.
red light. So I said, you double your standard deviation and subtract it from the mean. If you have a value that is positive, then that means that data is normally normally distributed. But if when you run it, when you subtract it, you get a value that is negative. Then that means your data is skewed. For example, let's say you run, let's say your mean is 30, mean weight 30, and then standard deviation plus or minus 5. So when you multiply, we say you should multiply that standard deviation by 2. So if you multiply 5 by 2, 10 from 30, you are going to get 20, which is a positive value. So that means that data is what is normally distributed. Also, you can use, but let's say, for example, if the mean weight is 30 plus or minus 18, the standard deviation now is 18. You multiply it by 2, it is going to give you 36. So 36 is, if you now say 30 minus 36, your answer is going to be minus 6. So that means, that shows you that means the answer is negative. So once you do that and the answer is negative, it tells you that the data is skewed. So that is simple test that even without using any calculator, any software, you can easily know that, oh, this data is skewed or this data is not skewed. But then you can also use statistical methods. You can use computer. You can use Shapiro-Wilk test. There is a test called Shapiro-Wilk. So when you do it, when you run the test, you can, SPSS, even Excel can do it. All you need to do is look at the p-value, because it is also going to give you the p-value. So if the p-value is greater than 0.05, that means there is no significant difference between the values. So that means your data is fairly normally distributed. But if you use it and the p-value is less than 0.05, it means there is significant difference between the values, that it is telling you that there are extreme values inside. And you know, yesterday we talked about extreme values. So once there are extreme values, the data is likely going to be skewed. So that will give you a p-value that is less than 0.05. So if you are testing for normality, you can use Shapiro-Wilk test, and that is how to use it. There is also Kolmogorov-Smirnov test. That one also, you can use SPSS to run the test and so on. So at least the simple one, just look at your mean and standard deviation, even without calculator. It can help you. And you can use graphical method also. When you plot the histogram, just plot the histogram for whatever you are trying to, if it is age. So plot the histogram of the age distribution. If it gives you a normal distribution curve that has bell shape, that is symmetrical, then it tells you that, oh, this is normally distributed. But when you plot the histogram and it gives you a curve that is not symmetrical, meaning that one side, it is skewed to one side, either to the left or to the right, it is telling you that that data is not normally distributed, is skewed. So
Thank you so much, sir, for the elaborate explanation.
any other question?
Yes, sir. This one from Dr. Alabere is saying, thank you so much, Prof. Sir, for this wonderful presentation.
Yeah.
Okay, that we would appreciate. Is just a compliment? Okay, the remaining ones are compliment. I don't know, is there anyone on the online that wants to speak? One can indicate by raising hand. I think so far these are the questions available. Thank you so much, Prof. Sir. On behalf of the Supreme Congress of ARD UDUTH, entire NADA at present and participants, I want to extend our sincere appreciation for this sacrifice. Thank you so much. When we approach you, we know that you have a very tight schedule, but you not only accept to carry us along, but also you put us through and you correct the schedule and add so many things. This is a huge sacrifice that I will never forget. Thank you so much. May Allah reward you abundantly and increase you in knowledge and wisdom. Thank you so much. Thank you, the participants, for showing off. Thank you so much. Thank you, everyone. Our last lecture next week will be on